Hey there, it's Max again. We're going to be going through the solution to Unlink. Hope you guys had a good time with it. I think it's a super fun exercise. There's also a part two to it that's equally fun, but a little bit harder. So we're going to get right into it. We're like normal. We're going to look at the solution in the start.py file. We're going to mess around with GDB, and then we'll go through the slides to make it a little bit more visually appealing. So the variables are actually right here, and they're pretty nice, but we're not going to use those. I'll talk through how all this works, and we'll get the values in GDB because that's fun. So the got entry for puts minus hex 18 is we want to put here. This will be the where we're going to write to, and the what is going to be the address of our shellcode. And conveniently, that's right here. We could just copy these in, subtract hex 18 on the where, and be on our way. But that's no fun. So let's play around in GDB with it first. I've also added automatic breakpoints for this one and many of the other challenges. This is because it's just nice to have breakpoints in important spots. So the things we care about are the address of shellcode. So we have that right there. So we can copy that. And the other thing we care about is the got entry for puts. Now, Pwnybug actually is really nice, and you just run the got command, and it will just give that to you. So we can just copy that. You're probably wondering why I'm not writing it right away. I wanted to show something that was kind of fun first. So we're going to do continue and continue, and then if you look at the heap, we can actually see this chunk here. You see that this free chunk actually has FT and BK written as the those values that we're doing. So you can see that use after free definitely is happening there. Now, if we do bins, we can also see that it tells the unsorted bin it's corrupted. This is true. I'm assuming Pwnybug has some black magic where it's just checking the links in the list and make sure that they're circular. So if we do another continue, then we're going to crash, I believe. And I've actually rigged everything to have the malloc source code without optimizations in here too, just to make it easier. And we can see that we're actually crashing at Unlink. And if we go even deeper and try to figure out like what command is crashing, we can see we're doing RAX plus hex 18. And this RX plus hex 18 is exactly what you'd think it is. It's going to be that FD that we're trying to write to. And if we do regs, scroll up a little bit, we can actually see that RX is going to be this big value. So it's doing that plus hex 18 and then crashing immediately. I think it's just really nice to visually see this, see it crash, see the heap. And so if you're triaging something in the future, you know what you're looking for. Cool. So we're going to write this up. So 404020 minus hex 18 to counteract that hex 18 we're looking at before. And then this is going to be the address of our shellcode once again. 45030. And this just turns off ASLR, so don't need to worry about that. Great. So we're going to do start.py once again. We're going to continue, and we're going to look at the heap. And we can see again that we've written the values we want. So this is the address of our shellcode. If we do p shellcode once again, we can see that these are the same. And then if we do got and we do minus hex 18, this ends up being hex 8, which means we do indeed have these addresses set up correctly. So now if we do continue, we can see that it gives us a little shell. So if I go up, that is wrong command. If I do who am I, we can see that we did win. We did get this set up correctly. Woo! All right, I got to cool down from that dopamine hit I just got from popping that shell. never goes away. So now we're back to the slides to actually show this visually. So as we talked about before, the vulnerability is going to be right here. We're going to have the use after free, so we're editing this. Now, like I said before, the flow is that we have the use after free, and then we free the chunk directly above unlinked chunk. And this is where the actual consolidation process happens. And that's the cool part about this. So we need the vulnerability to write the pointers and then a way to trigger the consolidation, which is with this free. I'll turn off my camera so we can see that image briefly. So remember, the FD is the where and the BK is the what that we're going to write. We're going to use the got entry of puts for the where and the address of the shellcode for the what. That's going to be FD and BK accordingly. And when we actually set this up to make it easier to read, we're going to set this to where and what. And the where is going to be the got entry for puts. What's going to be the shellcode. You guys have seen this diagram a million times at this point, but I still think it's worth kind of hammering home. So we're going to, the where of BK and what of FDs where these writes actually happen at. And that's the important thing here. So the what of FD is the reason that we can't just write to an arbitrary section, because we have to make sure that's writable. Otherwise, that write would happen and it would corrupt everything and everything would crash. Cool. So the tricky part is we need to set the where equal to where minus hex 18. And this is because we want to write to the particular location. If we don't do that, when it adds hex 18, it goes too far. And at this point, we just don't want the shellcode to corrupt, and so we just have to jump over that. Now, this offset thing is I think the hardest part of this exploit, and this is a really nice visual of it. If we were aiming for the got entry, it would go, and it's actually adding hex 18, so we want to go to that proper spot. So beforehand, we need to subtract it. Otherwise, we would go too far on it. Then we jump to the shellcode, and we win. Woo! Now the shellcode's super simple. It's literally just pushing the address of winner and then calling ret, which will then take that address from the stack and go to it. So I do have some bad news for you. Turns out that this was actually mitigated. I actually had to recompile libc in order to make this doable for this. But I don't think all is lost here. I think that this is a really interesting technique and it makes sense to learn about. This is one of the first exploit techniques and it was documented in some FRAC articles back in the day. The way this was fixed, though, is that it does a circular check. So it goes FD's BK equals P and BK's FD equals P. So it makes sure that we're in this circle. And if it's not, then it crashes and says, hey, there's been a corruption of sorts. I also think Unlink is hard from an exploitation perspective. There's a lot of misdirection, there's a lot of moving parts, and I think it's a good stepping stone to other things. Thinking about primitives is also important. So although this is mitigated, I think it is very valuable to learn. Yeah, thanks for going through the exercise. Hope you had a good time with it and have fun in the next exercise. Thanks.